All right, drum roll, please. On to the good stuff. Okay, so this really begins the course. So I will slow down a notch, although you can play these videos back at 2 times speed anyway. Although I'm not going to slow down to half speed. Nevertheless, so we'll slow down a little bit. We'll have more of a discussion. We'll talk about some things. And this, like I said, this really begins the course. So very important here. So the course really, all of calculus has two major parts to it. There's other stuff, of course, but the first part here is the derivative, okay, which obviously we have right here. This other part is called the integral, which we'll get to later. Both of these things, as part of their definition, depend on this idea of a limit. This is part of both, okay, which we see here. So as you can imagine, it's pretty important stuff, okay? There are really two fundamental pillars of calculus. The first one is the derivative, the second was the integral. Both of those definitions have limits in them. So it's very important that we understand the concept behind the limit, how to evaluate a limit, how that relates to the derivative and to the integral, okay? So we're going to do this in a very similar fashion. In other words, how I set this up with the derivative is going to be how I set it up with the integral is going to be how I set it up with any problem that we come across. So the idea here is there was a problem, and in trying to solve the problem, from that kind of came about the definition and the idea of the derivative and the integral and everything else. So let's kind of look at the problem. There are two problems, but they're really the same problem, which I'll show you. And then we'll talk about how to solve the problem. And the sequence is always the same. The first part is generally some sort of estimation or approximation. How do we approximate or estimate the answer here? And then the next part is, okay, how do we get a better approximation? How do we get successfully better and better approximations? And then from that, we develop a pattern or a definition to find the exact. So we're going to do now. So we're going to do every time. Okay. So the derivative came about as trying to solve this tangent and or really it's the same thing, I'll show you, or the velocity problem. So we'll look at the tangent one first. The idea is, first of all, what is a tangent line? So tangent means touching, okay? So it's essentially a line that touches a curve just once. And the question is, how do we find an equation of that line? Okay, so that's really the problem, this example here. Right? Let's try to find the equation of the tangent line to the parabola y equal x squared at the point 1, 1. So immediately we see a problem, because if I ask you for an equation of a line, whether it's tangent or not, what information do you need? Well, you either need 2 points or you need a point and the slope. And the only thing we have here is a point, nothing else. So we need to figure out or find a way to approximate the slope, okay? So let's go ahead and take a look at the graph here. So here's a graph of y equal x squared, and you can see the blue is the parabola y equal x squared. And the red is the tangent line, and P is that 0.11. So the tangent line, the red line, is touching the 0.11. And the idea is, how do I find an equation of this? So I want an equation of this. Okay, again, I only have 1 point, the 0.11. I don't have anything else to go by. So in order to figure this out, I'm going to have to approximate, excuse me, or estimate this. And what I'm going to have to do in order to estimate this is pick another point on the line y equal x squared to do that. And so I chose this generic point here, Q. Okay, so notice that Q is on the parabola. It's obviously not on the tangent line. But I can connect Q and P with a line. That's the black line there, which is called a secant line. Secant because it crosses 2 points, the point P and the point Q. Okay, so the question is this a reasonable estimate? In other words, given the point Q, if I calculate the slope of the line PQ, the secant line, is that kind of a reasonable estimate for the red tangent line? Yeah, it's okay. Obviously, PQ is a little steeper, right? This is a little steeper, this is a little shallower. It's not that big of a deal. It's not bad. It's not an outstanding approximation, but it's not bad. So let's say I did that. How do I think, or how do you think I can then try again and get a better approximation? Well, obviously I can take Q, and instead of putting it that far away from P, I can kind of put it over here, right? Closer to P. And then if I connect PQ with this line here, right, that'd be a better approximation. And you can see where I'm going with this, right? You can begin to slide Q all the way down really, really close to P. It is important to note that Q can never equal P, right? Because we do need 2 points. Now I can get as close as I want. There's some language we're going to revisit over and over, but never actually get to P. Okay, and so what I've done here is set up, no matter where I put Q, it's always represented by x squared. The reason, of course, being because it's on the line x squared. And so I can set up a slope for PQ as the change in y over the change in x. So that's where this comes from. As long as x isn't 1, because then Q and P would be the same, which we can't, right? Can't allow that. So we can, and by the way, there's nothing magical about having Q above. I could have had Q over here. That's also fine. So we can do this a couple different ways. From the right and from the left, right? So I can either start Q here and slide down that way, or I could start Q here and slide up this way. So let's make a, well, let's not, I mean, it's already made for you. Let's take a look at the chart I have here as Q approaches P from the right. So if I use this value of x, right? So if x is 2, then f of x is 4 because it's 2 squared. And so if I look at the point 1, 1 and 2, 4, I can determine the slope easily enough, right? It's just the change in y over the change in x, 4 minus 1 over 2 minus 1. And so that's where the 3 comes from. Okay. I could do the same thing if x is 1.5, right? So this would be 1.5. This would be 1.5 squared. I can do the change in y over the change in x. And we would see then that the slope is 2.5. I can get even closer, make x 1.1. And so y would be 1.1 squared, and I can do the change in y over change in x, and I get a slope of 2.1. So a couple questions here. First of all, how long can I play this game? Well, forever is the correct answer. But I really don't think I need to, because it certainly seems the closer I get to 1 from the right, the closer the slope gets to 2. Okay, everyone see that? We can also approach from the left, same sort of idea, right? So from the left, x values are below 1. So if x is 0, f of x is also 0, so the slope is 1. If x is 0.5, then f of x is 0.5 squared, or 1/4, and the slope would be 1.5. So you can see, again, you can play this game for as long as you want, but it seems like the closer x gets to 1 from the left, the closer the slope gets to 2. So it seems reasonable that tangent line slope should be 2. Okay. Okay, so this concept is getting closer and closer without actually reaching. Very loosely is what we refer to as a limit. And again, it's the most fundamental concept in calculus because it's very closely related to the 2 pillars. So it's very, very important that we understand what's going on here. So this section really is not how to evaluate them. The only thing at our disposal right now is guess and check, which is essentially what this was, which is fine. I just want you to be familiar with the concept. So we're just kind of scratching the surface here. We'll get into more detail, of course, as we go on. So we say the slope of the tangent line is the limit of the slopes of the secant lines, right? So the limit as Q, and again, that's red, approaches. The limit as Q approaches P of the slope of the secant line is equal to the slope of the tangent line. Or another way to say that is here. The limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. Okay, again, limit. Notice that x cannot be 1, okay? Because that would be a ginormous problem down here, all right? So we cannot allow x to equal 1. So the limit is about x getting closer to 1, okay? Which is really what that's related to. Let's look at a different problem, seemingly, but it's really the same thing. So suppose we drop a ball off of a building and the distance it falls after t seconds, which is denoted s of t, which is pretty standard notation for physics, measured in meters, is 4.9 t squared. So in other words, after 1 second, if you put 1 in here, it'd be 4.9 times 1 squared, or 4.9 meters. After 2 seconds, it would be 4.9 times 2 squared, etc. So I want to find the velocity of the ball after 5 seconds, which means exactly at 5 seconds, which is called the instantaneous velocity, and this is a problem. Is a problem because I don't have a formula for the velocity. The only thing I have is a formula for the distance. Okay. So we can calculate what is called the average velocity, right? If we take a look at the total distance traveled and divide it by the time elapsed, we do get what is called an average velocity. Okay. Now notice that the time, there has to be some positive time elapsed. Okay, that can't be 0. Cannot have 0 on the bottom. So I need some time, I need some time approximate, right? It could be large, like 10 seconds. It could be very, very small, like 0.0001 second. But I do need some sort of interval to deal with. That's the only way to figure out average velocity. So we're going to do this the same, right? Does this sound familiar? This is really the same thing as the problem we just did, right? How do you find the slope given 1 point? It's the same thing. How do you find the instantaneous velocity given 1 point? The point is 5 seconds. So let's take a look at the average velocity, let's say between 5 and 6 seconds, okay? So that would be the change in distance up top, right? So 4.9 times 6 squared minus 4.9 times 5 squared. And the change in time on the bottom is 6 minus 5, or 1. So you do that calculation, you get about 53.9 meters per second. Okay. Is this a good estimate? It's okay, I guess. Yeah, can we get a better one? Well, sure. Instead of between 5 and 6 seconds, maybe we can go between 4.9 and 5.1, right? If we tighten up the window of time, we'll get a better estimate. So again, right, again, does this look familiar? Yeah, it's the same basic thing we did before, right? So between 5 and 5.1, and again, how would I calculate this? That's S of 5.1 minus S of 5 over 5.1 minus 5. That would give you the 49.49 that's in the chart, okay? Again, S of 5.1 is S of 5.1 is 4.9 times 5.1 squared, right? You just plug it into the distance formula. If we tighten that window up to 0.05 seconds, we get this. Tighten it up a little further, we get this. Again, how long could we continue with this? Forever. But we really don't need to, because it looks like the tighter the time interval, the closer the average velocity gets to 49. Okay? Seems fairly obvious. So we can take a guess and say, yeah, at 5 seconds, it's probably pretty close to 49. Okay. Now, this is really summing up the section. Okay. It is very crucial to understand the difference between an average rate of change, whether it's an average slope of the secant line, an average velocity, an average profit margin, an average whatever. So there's a difference between an average rate of change and an instantaneous rate of change, okay? Average rate of change always requires 2 points, okay? And it is an estimate. The instantaneous rate of change only requires 1 point, and it is exact. And of course, we're going to revisit this because right now, this is all we know how to do, which is fine. But we want to go from here to here, right? I don't want to bother with charts and graphs. I want to find out the instantaneous rate of change exactly, requiring 1 point. As you may imagine, this jump is where the limit rears its head. Okay, so we will be talking a lot about this going forward. So really what I want you to get out of this section is it's important to understand where the problem came from, right? How do you find the slope of the tangent line if you only have one point? And I want you to understand this idea of estimating or approximating average rates of change. And then right now we just have a chart to kind of look at and kind of guess instantaneous. Okay, so you'll see here on the worksheet same sort of kinds of same questions. So this is all related. This is all related to this function. So again, average velocities you should be able to calculate. They're just fractions, right? To be for this first one, it would be f of 2.5 minus f of 2 over 2.5 minus 2, whatever that is. And then you do that again for 2 to 2.1, etc. And then this is just going to be a guess based on your work above. Okay, I'll post the key for that, and then you'll see the homework is actually fairly similar. Okay, average again. There's average, and then you're supposed to estimate, right? Estimate instantaneous. These are going to be guesses based on the previous work. All right, so enjoy that, and that actually completes the material for the first exam.